So in this lesson, we have an exciting moment in math where two things that we kind of know about separately come together in a really nice way. Those two things in this case are our limit notation and our rational functions that we've been working on. So I want to start just by reviewing these two ideas, just like what does this notation mean? And when does a limit exist or not exist? So we're going to complete both of these sentences together. It would be really smart to pause the video here and just in your head try to answer these two. Like this, how do we say this, and what does it mean? And when does a limit exist? So hopefully you said something like the limit of f of x as x approaches negative 9 equals negative 18 means that as the x values of f of x approach negative 9, the y values approach negative 18. And if you're thinking about something like from both sides, that is 100% correct, and we're going to capture the idea over here. So this limit exists only if the function approaches the same value from both sides, or another way we said that is if the left and right limits are equal. So that notation is going to be helpful as we go and describe our rational function. This is the same function we saw in the last two notes here, just to make our lives a little bit easier. We're going to describe this function with the limit notation that we're using up here. So just to review our function f of x, here I'm giving you the graph and the factorization because we've done this before. What we did, right, is we saw that our x plus 9 factors canceled out, and we kind of rewrote it as x minus 9 over x plus 10. Now, what that means, right, is we got this asymptote, we called this, at negative 10. And then we also said there was a hole at the 0 of the denominator that canceled out, which was x equals negative 9. And that hole, I believe, ended up being at negative 9 comma negative 18. So right down there. So let's draw that hole in because that's going to be useful to us. So let's go ahead and label these two. So this was a hole at negative 9 comma negative 18 and an asymptote at x equals 10. Negative 10. So those features we explored in a previous video, and you can check your notes from that video if you want a reminder of how we did that. Now, we can talk about the limit of this function wherever we want, but we want to focus at these two special areas. So the first limit I'm going to write down, we'll start with my asymptote. So we'll say that the limit as x approaches negative 10 of our function f of x, we'll say this limit does not exist because, notice my left limit is positive infinity and my right limit is negative infinity. So in other words, my left and right limits are not equal at x equals negative 10. And I can write that down in my limit notation. So I can say because, let's see, from the left, my limit is infinity. So notice I'm going up forever. And from the right, my limit is negative infinity because I am going down forever. So that's my first limit. So this is, could say this is the limit at an asymptote. And it does not exist. And then we can do the limit at our hole. So remember, this was also called a removable discontinuity. So let's say I gave you this function and I asked you to find the limit at x equals, as x approaches negative 9. My work for this, well, this would look an awful lot like our work for finding the hole, right? So I'd factor, and then I would cancel out my repeating factor. And notice that repeating factor was what was keeping me from plugging in the negative 9. If that x plus 9 had not been on the bottom, I could have just plugged it in. Okay. So notice the limit as x approaches this value of my hole is just the y value of the hole, right? So these ended up giving us the same value. So as we study these rational functions, we can use our limit notation to describe these features we already studied in the previous lesson. So we're always going to say at an asymptote, at a vertical asymptote, the limit does not exist, so because we get this feature where the one piece is going up forever, one piece is going down forever, right? And at the hole, Well, my function approaches the hole from both sides as I walk along the curve. So at the hole, the limit is just the y value. So really I would argue this is the exact same thing as your previous lesson. We're just kind of using different notation and calling it a different thing, right? But we're still working with factors that cancel out and factors that do not. Now, I'm going to highlight 3 different cases you're going to run into as you do your practice problems. So different ways these problems can work out, essentially. So if you're somebody who likes really specific examples that match the delta math, here they are. The first example is kind of the easiest example. So notice if I plug in -5 to my denominator, well, what do I get? -3 times -5 plus 3. That's a positive 18 on the bottom, right? And the only number that I cannot have on the bottom is 0. So this one's allowed. I can just plug this in. On top, right, I get -5 squared. We like to write that in parentheses. And I get 25 minus 1 is 24 over 18. So this would, if we wanted to simplify it, we would get 4 over 3. Okay. So that's my first example. And the reason I can just plug it in is as I look at the curve, we would be on a point on this curve that is neither an asymptote nor a hole. So like say this point right here, I could just plug in x equals -6. It would spit out a y value from my function. Say f of -6 is the same as the limit as x approaches -6. So that's sort of the easiest case. Watch out for those because sometimes you do that work of simplifying for nothing. My next case here I'm going to factor because I can't really tell if -7 is going to make my denominator equal to 0. I could plug it in if I wanted to check, but I have a feeling it's not going to work, so I'm just going to factor first. Top is a difference of squares. And then bottom, we're going to get, let's see, +7, -1. And then notice I have something that factors, and sure enough, I could not have plugged in that -7. And then I'm just going to rewrite my limit with that term canceled out. And notice what happens here. This one, I still cannot plug in that -7. So it still would make my denominator equal to 0 if I plugged it in. So this limit does not exist. So this is the case where we have an asymptote. So this would be like a limit at an asymptote case. And then my last case here, this is kind of a tricky factoring one, right? Again, I have this 4, and I know that 4 squared is 16, so 16 minus 16 is 0, so I can't just plug it in. I'm going to factor the top and bottom. Notice every time in my work, I rewrite that limit statement because I want to keep all of my equalities true, right? So I'm going to keep rewriting that limit statement until I actually plug in the value. Top factor is like this. It's just anti-distributing. Bottom's a difference of squares. And then I have something that cancels. And what do we get here? X over x plus 4. And now I'm plugging in the 4, so I don't have to write my limit anymore. I can go 4 over 4 plus 4. Same as 4 over 8, right, which is a 1/2. Okay, so this would be, in this case, this limit does exist, but I had to cancel out a term first. This is a limit at a hole. Okay, so those are the 3 cases you'll run into. I'm going to give them to you probably separate first, and then mix them all together on you.